Hello guys, welcome back to Trace Over Time. So this is going to be our fourth lecture on this series, Open Quantum Systems. Okay, so this lecture is going to be on density matrices. For when we want to learn about open quantum systems, like this is the mathematical formalism that is going to be followed. Okay, so this lecture is going to be about density matrices. Okay, so first of all, I'll give you density matrices. First of all, I'll give you like a tiny bit of a motivation of why to study density matrices. Motivation. Okay. Why do we need density matrices? And how do I use density matrices? What are density matrices? We are going to answer all these questions in this lecture. Okay. This lecture is going to be useful for any student of physics that has come up with the term density matrices. Okay. And it's going to be an introductory one, and as well as it is going to be very helpful for people that want to go deep into the topics, go understand the topic very well. And for open quantum systems, it's going to be indispensable. It's going to be very extremely useful, extremely necessary. Okay. So first of all, let's go with the motivation. I'll give you a very simple example, okay, a very trivial example, and I'll tell you why I can't use the wave function picture anymore to describe that system. Okay, so let's take an electron, just any electron, and we are going to study the spin states of those electrons. Okay, so let's say we have an electron. Okay, so what are the possible spins it can have in one direction? Like it can have two possibilities, one are up or down, or it could also have a third possibility, which is the superposition of up and down, right? So it has three possibilities. Let's say first one is psi 1. Okay, so psi 1 is up, and then the second one is psi 2, that is down, and then psi 3 is, let's take a like an equal superposition of up and down, right? So up and down. Okay, so these are the three possibilities that my electron can exist in. Okay, I've taken a system like this. I've taken, basically it can be any of the superpositions. I've taken only three of these possibilities. Okay, so it's like I have a system in which it could be either in psi 1, I have an electron which could be in psi 1, psi 2, or psi 3. But beforehand, from before, I have no idea what what state the system is in. Okay, so it's not, it's like it could be in the up state, it could be in the down state, it could be in the superposition state. I have no idea, and it's actually my lack of knowledge. It's my incapability of acquiring enough information about the system beforehand, which is causing this like unknownness in the value of the spin. Okay, so let's say I have this electron, and all I can know about this system is that it has a 1/3 probability of being in the up state, 1/3 probability of being in the down state, and 1/3 for the superposition, equal superposition. So let's say this has a p psi 1 of 1/3. This one also has 1/3, which is p psi 2, let's say, and this one p psi 3 is 1/3. Okay, so we have like a system in which it could be in either of those states, in any of those states, and then the weightage, the probability weightage for each of these states is 1/3. Okay, so what do we do? We can't possibly write such a system in the wave function form. Okay, we need to do something about these probabilities. and we can't do that using the wave function, right? So what do? So we need to insert a new kind of mathematical object called a density matrix, which will deal with this information for me. Okay, I don't have to use the wave function picture anymore for this. Okay, so let's move forward. So this is like a motivation. Okay, but for this case, let's say I want to write the density matrix. I'll give you the recipe. I'll explain it to you later why this is the formula for the density matrix, but this is the recipe. So let's say P1, P psi 1. Okay, P psi 1 is this much, P psi 2 is this much, P psi 3 is this much. So the density matrix is written, it's written as, is denoted as rho. Okay, density matrix. Rho, it's given by this formula. It has three possible states, so I equals 1 to 3, and then it will take the probability, let's say P of psi I in this case, times psi I. Okay, so this is the formula for evaluating the density matrix. Okay, so what will this look like? It's like P psi 1 times psi 1 times psi 1. So this is the cat times the bra, and the same for all of these. Okay, this is how you calculate the density matrix. So what will this look like? Okay, what will this look like? I'll do the mathematics for you, so for you to be able to do it by yourself later on. Okay, so you get what the formula is. I don't need to write the formula again. I'll just write it in the corner if you need it. So density matrix, it's like summation I. Let's call the probabilities as pi. Okay, and times psi I. These are the quantum states. These quantum states. The PIs are the probabilities of me getting those quantum states upon doing an experiment. Okay, so this is what the density matrix is, and what is it going to look like? Okay, so it's going to look like rho is P1. P1 is this much, 1/3 times psi 1 plus 1/3 psi 2 plus 1/3 psi 3. Okay, P1 equals to 1/3, P2 equals to 1/3, and P3 is also equal to 1/3. Okay, so this formula looks quite simple. Okay, so how do I actually compute it? I guess you guys know how to do all these things, but still I'll give you the example because it's going to be helpful for you later on in your quantum mechanical considerations. Okay, so let's see how to write this as column vectors. Okay, so psi 1 is basically psi 1, and this is a two level system, so let's choose a certain writing process. So psi 1, the up state, I'll call it as 0 1, and psi 2, I'll call it as 1 0. Okay, so I can also reverse what I call each other. It's a matter of convention. So psi 3 will be, for me, it's 1 over square root 2 of this one plus 1 over square root 2 of this one. So it will be just 1 over square root 2, 1 over square root 2. Okay, so this is my psi 3. Okay, now I need to compute these. Okay, so I'm going to erase this part. I'm going to keep this formula in case you start losing sense of things. This is an important formula which will make sense of later on. Don't worry. Okay, we'll explain it to you where this formula comes from. But this is the formula this is the most general formula for finding density matrices. Okay, regardless of pure state, mixed state, this is the formula that we are going to use all the time. Okay, so so how to compute this? So let's find the psi1 times psi1, this bracket thing, this ket times bra thing. Okay. So this is just ket 0 1 times 0 1. This is just 0 0 0 1. If you do it in your copies in notebook, you will be able to figure it out. And if you're a student of quantum mechanics, I assume that you know already how to do this, but even if you don't, there's nothing to worry about. It's very simple. So psi2 times psi2, this is just this one, 1 0 1 0, and this will be just this one, 0. Okay. And now psi3 times psi3, this will be over square root 2 1 over square root 2, this 1 over square root 2 1 over square root 2, and what will this give me? This is just half times half times half. This is half. I'm sorry, it is getting a little, because of my perspective, it's getting a little like this, and I apologize for this. Okay, so this is just the ket of 1 over square root. I can just write the 1 over square root outside. I can take it like this, 1 1, and then 1 over square root 2 1 1. So what I've done is I've taken the 1 over square root 2 outside of this. You can do this. It will just become half times bigger matrix 1 1 1 1, which is the same as half 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 half, right? Okay, so can you see what I'm writing? Yeah. So I found the forms of all these things: psi1 times psi1, psi2 times psi2, and psi3 times psi3. Okay, so these are the forms. So let's start adding up all these things. Let's just keep what I found. I found this one, and this one. So let's erase the rest of the stuff. Let's erase this part also, because I need to write. Okay. So this is my. It's a little haphazard. I hope it's fine, because I don't have enough space. This was this thing, and this one was this thing. Psi2 times psi2, and this one was my psi3 times psi3. Okay. So what was the formula? It was just 1/3 of this one times plus 1/3 of this one. Okay, plus 1/3 of this one. Okay, so the density matrix is something like 1/3 0 0 0 1/3 of this one. Remember? Okay, I wrote this one first. Anyways, it doesn't matter. So 1/3 of this one first. So it's 0 0 0 1 over 3 plus 1 over 3 0 0 0 plus 1 over 3 of this. So 1 over 6 1 over 6 1 over 6 1 over 6. So what will this give me? Okay, in this position and this position, I will get stuff like 1 by 3 plus 1 over 6. So what is this? This is 6, 2 plus 1, that is 3, that is half. So in this position, in this position, in this position, it will be 1 by 6 plus 1 over 3. In this position also 1 over 6 plus 1 over 3. And then the rest is just 1 over 6. Okay. So the final matrix that I get will look something like this: half, 1 over 6, 1 over 6. Okay. So this is how you write a density matrix. This is the density matrix for the system that I talked about. Okay. So my system with three possibilities that I don't know what because of my own inability. Okay, it could be either plus the up spin or the down spin or the superposition of up and down. Okay, so such a state, when we learn a little more, when you go a little more into this topic, we'll get to know that these are actually called mixed states. Okay, most of the states in the universe are mixed states. It's very hard to keep like a pure state isolated. Okay, so mixed state means I simply don't know what the system is in, but I know the probabilities of finding a certain pure state in this mixed state. Okay, this ensemble of pure states, which is also you can call that a mixed state. Okay, so this is the representation of my system in a matrix form. Okay, so this is the reason that we use density matrices to talk about systems that we don't know much about. Okay. Okay, so let's explain the concept with with a little more mathematical rigor and with a little more general terms. Okay, so let's take an ensemble of pure states. What do I mean by that? I mean by that system whose state I don't know, and I only know what states it can be in, and I also know what probabilities it could have associated with what states I could find. Okay, let's say, so let's give you like uh, let's say we have my states. My states are given as, let's say, psi I, where I goes from 1 till 10. So these are the states I have in my unknown system. These are the possible states I have in my unknown system. And each state, psi I, has a probability. Let's say probability of the state to be, state being psi I, psi, it's qi. Okay. So this is what I know. This is what I know beforehand about the system. That I have all all these states, and also all these possible states, and the probability of the, the state to be in one of these states, or one of the state that is psi I, is given by qi. Okay. So let's. So this is called an ensemble. A pure state ensemble is sometimes given using this notation. So the ensemble is the notation for ensemble. Notation for ensemble is just probabilities with the states, possible states, and 5 goes from 1 to n. So this is the symbol from my, this is the symbolic representation of my ensemble. Okay. So what do I do? Now I take, let's say, so this is, I described my system already, so let's rub it. Let's hope that you noted them down if you're taking notes. But if you're, even if you're not, then also it's quite simple. I'll write the system details here. So if I just write the ensemble notation, it will be clear to you. So my ensemble is just given as qi, psi I, and I goes from 1 to n. Okay, this is the ensemble that I have, right? So let's say I have taken the system and it's psi I. Let's say it's in the ith state. Okay, so I have taken the, well, I already know that the state is in psi I, but now I have to do the measurement. Okay, I have taken the ith, prepared the system, let's say, whatever you can say, in the ith state, and then I'll do a measurement on the system. So we did this earlier in the earlier class. Okay, so in this part, I mean, it would be helpful if you go to the earlier lectures of this series, which you can find on our YouTube channel. And even if you don't, then bear along with me, and you can learn about these things later. Okay, so the thing is, if I have, let's say, a state psi I, and I do a certain measurement on the state, So what it does is it takes this my system and it multiplies a certain matrix to my system, and k times I divided by probabilities. Probability of finding, let's say, k, given that the state was in I. Okay, so this is my initial state psi I, which I got from this ensemble, and then I did a measurement on this state upon measurement. So it is this one. Okay, so we are going to define it as psi k superscript I subscript, like this. So this means that this is the kth state. This is state that I get upon the kth measurement. Okay, on the ith state. Okay, so this is the state that I get. Let's say I have taken the system, the state psi I from here, and I do a measurement on it, and this is what the state collapses to with probability this one. This we've learned about these things in the earlier lecture. So if you have any doubt about quantum measurements, if you don't understand quantum measurements, I would suggest you to see my earlier lecture, at least the introductory part, because I'm not talking about POVMs. That lecture has lots of other stuff as well. So this is what it is, and this is the probability of the of the state for to collapse in the kth this thing psi ki, given that I is my initial state. Okay, so pki, what is the mathematical form of this? Is just psi I mk dagger mk psi I. Well, the mk's are just the measurement operators. They have certain properties. They have just one property, which is the if you remember that all the possible measurements from k to whatever, let's say n or whatever. I'm just reminding you of what it was. Mk dagger mk, that is identity. It has this property. Okay, and various other things, considerations which you will understand, which you will. I mean, if you look at my last lecture on this series, you will. These things will get clear if you haven't watched it yet. Okay, so this is the probability of finding the state in the kth. Collapsing to the kth state, given that I had prepared, it was prepared in the ith state from this ensemble. Okay, so this is what it is. So let's remember these things. Actually, we'll write this formula as well in the side, which I do for stuff that are important, right? Sorry. Okay, so this formula pki is just psi k psi I mk dagger mk and psi I. So this is another important formula that I might need to use later. Okay, so let's say, so this example was kind of trivial because we already took the psi I from the system, right? We didn't okay, can you see better now? I hope. I apologize for this. Okay, so this system is pretty simple. We already took the psi I from there, and then we did this certain thing. We did the measurement using the mk operator, and then it collapsed to this state with this probability. Now let's take the ensemble itself, and we don't know which system we have. Okay, we have the ensemble, and we have the knowledge of the probabilities of finding the particles, finding the system in each of these states. We know the probabilities associated with those states. We know what the states are, but we don't know what state it is in. Okay, so let's do this now. Let's do this now. So now in my initial state is the ensemble itself. In the first example, my initial state was psi I. Now my initial state is the ensemble itself, which is I don't know. I only know the probabilities and the states, possible states. Okay, so this is my initial state, and I do a measurement on it. And let's say, uh, okay, so I'm sorry because of these technical difficulties. Okay, so the probability of finding the outcome k, given that the system was prepared in a certain state psi I, an arbitrary state psi I. Okay, so probability of finding the outcome k. What would be the probability of finding the system in outcome k? This is the outcome k, which is given as psi I k, if you remember. Okay, so this is the psi pk is pki, which is the probability of finding k, given that I was the initial state. Now, what's the probability of finding pk itself? So any possible I could be the initial state if I get pk, let's say, if I get psi k. So pk is given as summation of I. It could take any, it could be in any of the I states, times the probability of finding it in the I state. Okay, so it's kind of critical here. So in this ensemble, I pick up a state. Okay, it could be in any of the ith states. And given that I got the ith state, an arbitrary ith state, the probability that the upon measurement I get this kth state is given by this pk. Okay, uh, given this is the probability of finding pk, and this is the conditional probability of finding the k, given that I have a state I. And why is the summation? Because any state, any initial state psi I could lead to the measurement of psi k, right? So I need to sum over all those possibilities, which is why I need to do this summation over I. Okay, so I know what this thing is given by, it's written there. So this is just the summation of I of qi times, this is I'll write a compactified form of this. So let's write this step as well. So this is just psi I mk dagger mk psi I. Okay, qi times this thing and summation. Okay, so now we, in the last class, we talked about a certain formula which is also very important. I'll again write this one also. It's an important formula about expectation values. Okay, so what was the formula? Formula was that psi a psi trace over a psi psi, and this is also the formula for expectation value. Okay, so what would this be? So this is, what is this? This is like let's say a diagonal matrix psi I, like all the elements of a diagonal, each multiplied by these qi's. Okay, right? So this is like an matrix written in the basis psi I. Matrix, this mk dagger mk is a matrix written in this basis psi I, and each of the diagonal elements are multiplied by this numbers qi. Okay, so I can write this using like this. So you can, it's like this matrix. It is a matrix times where qi is multiplied by q1 q2 times, let's say psi 1, this one, and this one is like psi 1 mk dagger mk psi 1. If here it will be psi 2 mk dagger mk psi 2, and like this. Okay, so it's a sum of all the diagonal elements of this matrix. But what will the ith element? It will be qi times, I am writing this so just to give you an idea. Okay, it's very simple. I I understand that you know that how to do this, but to make things a little more, so that you don't get uh, confused later on. Okay, so this is what it is, and this will give me this I of mk dagger mk psi I till n, this nth element. So this is like the sum of all the diagonal elements of a certain matrix. And what is the matrix? Think about it. It's very simple. So what's the sum of all the diagonal elements of the matrix? It's a trace. So this is the trace of this matrix. Okay, trace of mk dagger mk times summation I qi psi I psi I. Okay, so it's this thing. So from this idea, I think you can get, so you get this matrix. So we got all these matrices with q1 q2s and all these things multiplied in the diagonal. We can also write this one as this thing, which is you can say q1 times 1 0 0 0 0 and 0 everywhere, plus q2 times in the second diagonal element 1 and the 0 everywhere. So this is like q1 times psi1 psi1 plus q2 times psi2. I give you it as an exercise. If you don't understand this, I've given you a really small explanation, but if you don't understand this step, think about it, express it term by term, you will get it. Okay, so this is what the expression I'm getting from here to here. Okay, so anything familiar about this formula? Anything? I've removed it, but let me ask you this: does it ring as something familiar? So yeah, it's a density matrix that we learned about in the formula of density matrix that we learned about initially. Okay, so how did we get it? We got it using using it by taking an ensemble and doing a measurement mk on it. Okay, so from that formula I'm getting the form of this particular thing. Okay, the probability of finding this state in the kth state, given that it was in any arbitrary ith state, is given by this formula, and we are getting that we get this formula for density matrix here. Okay, the probability of finding the particle, the system in the kth state, the system falling to the collapsing to the kth state. Okay, so this is the density matrix. This part. Okay, it's a very important formula again. This is the one that I should have kept. So rho, the most fundamental formula of, most general formula of density matrix. Okay, most general form of density matrix. You can express pure states using this, express mixed states using this. So this is what I'm getting. Again, let's see. Yeah, let's. You remember this? If you saw the last lecture, you remember this concept of POVMs. We define these matrix elements. We define these elements, POVM elements, corresponding to separate different measurement outcomes, which are in the case of at the basis is not orthonormal. Okay, we use this certain kind of generalized measurements called POVMs when the summation of the EKs will be 1 and all that. So what was the definition of EK? It was MK over MK. So this we can write in the form of POVM as well. EK times rho. Okay, but EK is just the POVM element. Kth element. Okay. So let's move forward. Okay, so let's say we have this ensemble which is given by this. This is my ensemble with probabilities qi and psi I, and I've done the measurement on it. And I've in the last this thing I showed you the probability of finding the mkth measurement acting on it. It was given by this formula, which is pk, and it's given as I'm sorry, this tiny mistakes keep happening. Trace over mk dagger mk times this thing, the density matrix I qi mk. I'm sorry, it's just psi I. Okay, so this is what it was. This was pk, and this is the same as trace mk dagger mk times rho. Okay, so this is very important. This formula, this part pk is this thing. Now, what about the state that I will get upon the measurement? Okay, so I had this. My initial state was, you can say, I told you about the density matrices again and again. So I can say that my initial state can be represented as the density matrix. Initial state is the same as saying this one. With psi i's with qi probabilities qi's. I can say that my initial state was the density matrix given by summation I qi psi I psi I. Okay. So upon measurement, upon doing the kth measurement, what is my final state? Okay, what final state do I get? So that is the question now. Okay, so this is like a little recap, even though it was not required. I just did it for the sake of not losing track, because these things are kind of tricky, these examples. So so what would be my rho k? So I took this rho I did the measurement. Upon measurement, what would be my rho k? What would be the form of rho k? Okay, so this is what we're going to derive now. Okay, so let's start. So rho k is just basically summation of, let's say I got the kth state, I got the kth measurement acting upon my ensemble, and then what is the probability that, given that I have the kth state, what was the probability that it was prepared in the ith state? Okay, so it's given by this thing, so it's quite subtle. Okay, I found the system in the kth state. What's the probability it was in the ith state? It was prepared in the ith state. Okay, so the probability, that would be the part of the probability part of the density matrix, this part. Okay, and this is psi I k. This means that k has been prepared given that I was the initial state. Okay, so this is the density matrix that are the final density matrix upon measurement. So k is upon measurement and initial was I. Okay, this is the probability that I get k. There is the probability that I get k, but what was the probability of I state having been prepared in I, given that I get k? This is the probability of that. Okay, so we're going to use something that we learned in our high school or maybe in college also, in our mathematics course. So the Bayes formula basically. So what was the Bayes formula? Let's write it here. The base formula is, it was just that P, let's say I'm writing it like this, okay, P I K, okay, I, probability of the state having been prepared in I given that I get K, it's given by PKI, probability of finding K given that it was prepared in I, okay, times probability of the state having been prepared in I divided by the probability of finding the state in K. So this is just the basic Bayes rule that we have learned earlier. Okay, so we're going to apply it here. So there's a summation I here. So this is going to result in summation I. Let's apply this one. So it will take the form of. We can expand this one first. Okay, let's expand this one first. Let's. What was this thing? We learned about it. We showed you. I showed you what it was. It's like what's the K? The kth state, given that I was the initial state, and it was given by this formula, right? So psi I k. The form is just. It was in the initial part of the lecture, if you remember. By square root of p k I. This was what we did, what we found earlier in this lecture. So I'm going to use this here. Okay, I'm going to use this here. So what will this give me? This will give me. So this is Bayes rule. Bayes rule. And if I use this formula here, what do I get? I have to write a little smaller form. So this will be mk times psi I by this thing. So mk times psi I by the square root. I can write the square root later, and this will be, since it's in the opposite way, so this will be just psi I mk dagger by. So there's a square root here, there will be a square root coming from here, there will be a square root coming from here as well. So it will give me finally pki. Now I can use the Bayes rule. Pik by pki. So pik by pki, it's just pi by pki. Pi, what is pi? It's just qi. Qi over pk times this thing. Okay, psi I mk dagger. Okay, this is summation over k. Okay, now we can see that we can do a certain grouping, a certain familiar kind of grouping here. Okay, I can write this as summation I 1 over small pk times mk times. I can take the summation inside it actually, because this is this thing. Sorry, I can just take the summation inside, and this is mk, and then take the summation inside, qi psi I times mk dagger. Okay. Again, what is this? Familiar form. You can't see it properly. Yeah. What is this? This is a familiar thing that we've been talking about for so long tonight. So this is a row. So what the final state that I get is, it looks something like this: mk row, mk dagger. Sorry, it's a, you can say it row I, call it row I or whatever. So let's just call it row. So any row that falls into row I. This is pk. Okay, so I took a row and I did the measurement, and the state upon measurement is this one. Yeah, this is the state upon measurement. Okay, so I can also write it as, if I can just use the formula for pk, which is this one, and we can use the trace form of this formula. This is not exactly pk, this is pki. We had written the pk formula somewhere. uh, yeah, it's just we did it in the earlier part. Okay, so it was this thing. Okay, it was something like this. Okay, it was pk, it was this summation I qi and psi I mk dagger mk psi I. That was the basic one, and we from this we found out the more fundamental, actually the developing thought behind the idea of a density matrix was that we found that pk was actually trace mk dagger mk times rho. This is what we found. Okay, so this is an important one, and we should note it down. It's one of the important. This only applies to this one. This is one of the important formulas, important identities. Okay, so what was it? It was pk is trace over mk dagger mk times rho. Okay, so I can just put this formula here as well. So what does it give me? It will give this from here to mk rho mk dagger. Rho is just rho I, any initial row, by trace over mk dagger mk times rho. Okay, so this is a very important development. I'm sorry about the camera angle tonight. So this is a very important formula. This is what my upon measurement what I get as a final density matrix. Okay, as the density matrix upon the measurement. So this is something that you should be noting down if you're taking notes. It's a very important formula. Let's write it down here. So it was rho k. Rho k is the mk rho mk dagger by trace over mk dagger mk times rho. This is the final state we get upon measuring the initial density matrix, upon measurement of the initial ensemble. Okay, so this is the formulas. This is the formula of the final density matrix that I get upon the measurement of my initial density matrix. Okay, so let's move forward. So we have talked a lot about the density matrix. So initially we gave an example, a little example of how to deal with density matrices, why density matrices and all that, and how to find for a simple system. Now we are going to talk about the properties of a density matrix. Okay, so the properties of a density matrix. Properties of a density matrix. Properties. So number one. So what was number one? Number one property of density matrix is it has unit trace. Okay. What do I mean by unit trace? It just means that the trace of the matrix of my density matrix, the sum of all the diagonal elements, it has to be one. Okay, so density, it is one of the properties of the defining properties of density matrix. Okay, so can we prove it? Let's try to prove it. So the property is, let's use this color only. Trace of our density matrix has to be equal to 1. Okay, so proof is very simple. So rho, this is our density matrix given by summation I qi psi I times psi I. Okay, I want to take a trace over this thing. Okay, so how do I take the trace over rho? So that is just summation I qi trace over this matrix part. Okay, so this is the matrix part of this expression. I take a trace over this thing, trace over psi I times psi I. So what is this? It is just a big matrix with, let's say, a diagonal element in the ith place. We have a 1 here, the ith diagonal element. The ith diagonal element, and we have 0 everywhere. 0 in all the other places, right? So what's the trace of this matrix? It's just 1. Just this tiny 1 here. So trace of psi I is just 1. Okay, for any I. So this is just going to give me summation I qi. Okay, now what is qi? Qis are the probabilities, and summation of all the probabilities has to be 1 for all the events. So this is just 1. So hence proven. The trace of rho is equal to 1. Okay, this is proven. So let's go to the second one. Second property, this thing, property of a density matrix, of a density operator, you can say, is the hermiticity. Okay, so density matrix should be Hermitian, which is just how do I call it? Unit trace. Then hermiticity, which is equals to rho. Okay. Hermiticity. Again, we can prove this very easily. We can just write the formula for density matrices I and qi psi I. Then we take the Hermitian conjugate of this. We get I qi star. And then same thing, psi I dagger. This brow will become a cat, and this cat will become a bra. It will give me the same thing. It's like a projection operator. Okay. So this is, what is qi star? What is the complex conjugate of qi? It's just same as qi, because qi is real number, because qi represents probability. Okay, so this is the same as rho. So rho is Hermitian. We've proven that as well. Okay, so what is the third property of density matrices? That they are positive definite, which means that for all vectors V, let's say, belonging to a Hilbert space H, the density operator rho has this property, this thing, V rho V greater than equal to 0. Okay. So this is positive definiteness. Okay. Set as positive definiteness. Okay. So these are the three properties of density matrices. And another thing that is important here, like, oh, I haven't proven this one. It's very easy to prove. Wait, I'll show you the proof of this one. How to prove this one? It's nothing. It's just write the row, and you can just write the row as this: V I Q I psi I V. Okay. So what will this give me? Psi, this thing will be getting multiplied here, and this will be getting multiplied here. So this is like Qi summation I Qi. It's like mod of psi I V this squared. Okay. Right. And these are always positive. These are probabilities, and these are also always positive, like naturally. So this is greater than equal to 0. It's pretty trivial. Okay. So we got these three properties of density matrices, that they have a unit trace, they're Hermitian, and then they're positive definite. Okay. So let's move forward. Let's talk about okay, so the next part, we're going to talk about the dynamics of the density operator. Okay. Let's give the heading dynamics. Density matrix or density operator, whichever way you call it, doesn't matter. Dynamics of the density operator. So about the wave functions, what did we learn? We learned that there were two equivalent ways of expressing the time evolution of a wave function. So one of them was using the Schrodinger equation. The other one that we were talking about this thing, it was using the time translation operator. Okay, so two equivalent descriptions of the pure quantum state. Okay, of the time evolution of a pure quantum state. One of these was this: psi t goes as ut times psi 0, and the equivalent one, this is sign for equivalence, it was that psi t dot is minus I h for h cross equals to 1 of psi t. Okay, let's delineate this part. Okay, this is our this was the two formalisms, you can say, we were considering about the time evolution of the pure quantum state. Okay, so let's use both of these to see how the density matrix, how rho t evolves with time, the evolution of the density matrix. Okay, so let's first use this this part, isn't the time evolution operator. Okay, so we can write the rho t. We have written this many times already, summation I, but now the psi t's, they are time dependent. Okay, so instead of psi I, I'll just write psi I t times psi I t, right? And psi I t would be given by this thing, so it's summation I. I'll use this formula, and that would be qi ut psi I 0 times This is where ut dagger will be multiplied, I0 times u dagger t. Okay. So in this step we can see that if I take the summation, if I take this part of only this part of the summation and with the qi inside, we can just write it as ut summation I. Let's say, let's write down the steps. Psi I0 I0 times u dagger t. Okay. So this is just ut times, what is this? This is a very simple, it's just the initial at t equals 0, the density matrix at t equals 0. So this is rho 0 times u dagger t. So this is rho t. Okay, this is one of the important ones, expressing the dynamics of the density operator. Okay, now we are going to use this part. You can note it down. So this part takes a little different form. Okay, the Schrodinger equation, it gives me a little different form. So let's do it. Let's just take the rho t and then do the time derivative upon it, partial time derivative. Okay. So rho is this one, and the psi i's will be depending on time now. So if I take the time derivative, it will look something like this. So del t of this thing, summation I qi psi I of t times psi I of t. Okay. So this is just, so this is my rho dot t, and it will look like summation I qi, okay, del t psi I t I t turn by turn plus psi I t times del t psi I t. Okay. So this is expanded it using the derivative formula for derivative of product of two functions. Now this is just, I can use the Schrodinger equation here. So d psi dt, I can use this one here. This is just the opposite of the Schrodinger equation. What would that imply? Opposite means the complex conjugate or the Hermitian conjugate of the Schrodinger equation. So it would just be this thing. It would give me plus I, and then this one psi t, and the h would go this way. And h dagger is h, so it's Hermitian, so the dagger is not coming here. Okay. So using this, I can write this. Let's erase the rest of the part. Let's erase this part also. So we're going to use the Schrodinger equation here and here. Okay. From that we get this thing. T equals summation I qi minus ih psi it plus I psi it h Okay, and this is the same as minus I H summation. I'm taking the summation inside. Okay, so this could cause a notational difficulty. Okay, so this would, like, there's a complex number I here, but this I is only indicating the probabilities QIs. Okay, the states, I mean the states psi i's and the probabilities are the QIs. So this I are my states, and this is just the complex number. So don't complicate the two. Don't get confused between the two. I can write it like this. I'm taking the QI inside. It's very simple, and the H outside. Sorry, IT. Okay, minus the summation I again QI psi IT psi IT the H outside. Okay. So what did I do this? Why did I do this? So this part is our usual, like, again, our familiar form of a certain thing that we've been calling density matrix till now on. Okay. So this is a density matrix. So what do we get from here? We get that this is minus I H times rho minus rho times H. So what do I get? We get that rho dot T is minus I H comma rho. Again, very important formula and kind of familiar as well. If you've studied about density matrices even a little bit, you have seen this formula, I believe, and it's very similar to the a certain formula that we learn when we don't use density matrices as well. When we are just dealing with wave functions. Do you remember the name of the equation? A certain scientist, his name starts with H and ends with G. Yeah, Heisenberg equation. It's the same as the Heisenberg equation, but for rho. So this is actually called, this formula, this identity, it's called the Louisville von Neumann equation. Louisville von Neumann equation. Okay, so it's this one. It's what it's called. Okay, so we've learned all these things about density matrices, and now is the time to recall the postulates of quantum mechanics, and we need to reformulate the postulates of quantum mechanics, and express them with the help of density matrices. Okay, and do the same treatment as we did for wave functions in the case of this thing. In the case of wave functions, we're going to do the same for density matrices. Okay, so we're going to write the postulates of quantum mechanics once again. Okay. Okay, so the first postulate, like where does my state exist? Where does my wave function exist? It's a vector. It's a ray. More technically, it's a ray, but you can say, like, roughly, it's a vector in the Hilbert space. Now, what space does my density matrix exist? Okay, so it exists in the space of operators. So you can define a vector space. It's an interesting concept. You can define a new Hilbert space But instead of the vectors, usual vectors with the direction, my vector space will have its vectors as the density matrix, and they will be representing the states. Okay, so my new vector space will have its own definition of length of vectors, of norm, and its own definition of scalar product and all that. Okay, so it's on you. I'll give you the this thing, the task to verify that whether this space is actually a Hilbert space or not. Okay, you can try to verify it by yourself. It's quite simple if you know the definition of vector space and then further on Hilbert space. So my new space is where my rows are the vectors, the density matrices are the vectors, and this is called the Hilbert-Schmidt space. Schmidt space. Okay, so how is it defined? It's defined as the space of linear operators row such that space of linear operators row such that, what are the properties of row? Trace of row is equal to 1 and row, this thing is the positivity, right? Now the inner product, we have to have an inner product since it's a new space that we're dealing with. The inner product is defined as something like this. Again, you need to verify that whether it is a real inner product, and go back to your classes, linear algebra classes, and verify it for yourself that it is a real inner product. Let's say we have two density matrices A and B. This will be the inner product between the two density matrices. This is the definition. Okay. So A and B are the linear operators with these properties on the same space. Okay. Acting on the same Hilbert space, actually. They act on Hilbert space, but they exist in this Hilbert-Schmidt space, supposedly. So this helps us in defining the length of of our vectors in the Hilbert-Schmidt space in a new way, and this we'll use this one only. So length is given by this norm, which is like, this is the square root of the square of this thing. So scalar product, square root of the scalar product. This is given as square root of p also. Okay, so what will it be? Trace of row dagger times row. Okay, this is I'm talking about the length of row. The trace of row dagger times row, dagger times row is the trace of row square. Okay, so this is an interesting, this is a very interesting part. So this quantity, trace of row square. Okay, so this describes how pure my quantum state is. It turns out that row square is equal to 1 for states that are pure. And what do I mean by pure states? Pure states, if I have a pure state and I know that this is, I don't have any ambiguity like this probability to this state, this probability to that state. I know that it is in this state. Okay, that's what a pure state is. But if it's mixed, then I only know that I have a certain probability to find this state and then another probability to find another state. But when I have a pure state, I know that this is the state. Let's say I have a psi1, then I know it's psi1, it's a pure state. So I can write in ensemble language pure state as something like this. Okay, so this is for the mixed state, general state with psi i's with the probability q i's. For pure state, it will be just 1. Okay, with 1, the full probability is for 1, for one state. Let's say whatever psi, sorry. So whatever psi, we have this. This is how my ensemble will be written for the case of pure states. Okay. So this is trace row square, and it will be equal to 1 for pure states and less than 1 for mixed states. Okay, so this is how trace. But can you prove this? It's actually very easy to prove. And should I? I think I should leave it upon you that I can prove it. Let's show it. So another thing. So this trace rho square. I told you this is the length of rho from the center. So if this is equal to 1, it means that at unit length, it can't go greater than 1, remember. So all the space is inside of a sphere. So in the surface of the sphere, the trace rho square equal to 1, that's where pure states exist. And inside of the sphere, the trace rho square is less than 1, that's where the mixed states exist in this space. Okay? And the space is defined by all of this. So this is an important and interesting thing about pure and mixed states. Okay? So this is the first part of where. Let's go to the second part. What was the second part? How do I compose? Like, how do I combine two subsystems into one system? The answer was for wave functions. The answer was tensor product, and for my this thing for my density matrix, the answer is unsurprisingly the same. Tensor product. Okay. To combine two spaces, let's say we have two subsystems A and B with this is the density matrix for subsystem A, this is the density matrix for B. And for getting AB, I need to do the tensor product between rho and rho B. This is just, it's very simple and it's the same as earlier. No need of restatement. Now, evolution, time evolution. So the density matrices, they evolve as the Neumann, this thing, Liouville-Neumann equation, minus I, H, comma, rho. So this was one of the things, this is one of the identities telling me about the evolution of my density matrix. And another one was this thing, equivalent to this one, which is just ut rho 0 u dagger t. Okay, so this is equivalent. This is the time evolution part of the third postulate, which deals with time evolution. This is the third postulate in terms of the density matrices. Now the fourth postulate, what measurement? So I'll just write in brackets, combination of subsystems. This is time evolution. Okay. Fourth one was about measurements. And what did we learn? Is that in general measurement operation done on a certain rho, it will a general measurement mk. It will take my system to mk rho mk dagger by pk, which is this thing. I wrote this already. Mk dagger mk times rho. Okay, and this is also called pk in this part. Okay, this is the fourth, the measurement postulate. And pk, what's given by, did I write? Yeah, pk is given by this thing, and rho k is this thing. Okay, so these are the four postulates written in terms of density matrices. Okay, quite simple. Okay, so I'll give you another example. Okay, about what? About how to calculate density matrices, and the thing is that let's say I have two separate systems, and I calculate their density matrices separately. but they come out to be the same. Okay, it can happen sometimes. Then are these two different systems or the same system? Okay, did you understand my question? It's like I have two systems, okay, and they're giving me the same density matrix. So are these two the same systems or different systems? The answer is there is no experimental way to distinguish really. So we call them the same states. I'll give you one such example. It's a mathematical example. It's just example. Okay. So let's say we have one system which is given by, let's say, 0 and 1. This is my system 1. And then system 2 is given by this A and B. So these are 0 and 1 are our usual, this thing, like 2D Hilbert space, like this stuff. And AB, these are actually the superpositions of 0 and 1. Okay, my system 1, it's in a mixed state, and we know that the probability of the system to be in this one or this one are given by these things. So probability for 0, probability for 0th state is given by 3 over 4, and for the 1st state 1 over 4. And for this one, probability for A is given by half, probability for B is given by half. Okay, so these are the two systems that I get, and A and B, they are actually superpositions of 0 and 1. Okay, so what are the forms of the A and B? So form of A is just this, square root of 3 over 4 times O, 0 plus square root of 1 over 4 times 1. Okay, and B is just the minus of this thing, 0 minus square root of 1 over 4 times 1. Okay, so this is my system 1, 0 or 1. It has 3/4 probability of being in 0, 1/4 of being in 1. The second system is half probability of being in A and half probability of being in B. Okay, so let's write the density matrices for the system 1, let's say. So let's use our usual the notation, like 0 is just let's use it as this thing, and 1, again, it's a convention. You're chosen to do whatever you like, choose whatever notation you like. So in this notation, how do we express A and B? How do we express A and B using this notation? It's just 0 times this thing, so the upward one, and 1 times this thing. Okay, so it's just root over 3 by 4 and square root of 1 over 4. And this is just the opposite, root over 3 by 4 minus square root of 1 over 4. And this is the same as actually root 3 by 2. This is just half. And this is again root over square root 3 by 2. This is minus half. Okay, these are the forms of A and B. Now what do I do is find the density matrices. Let's find the density matrices of the matrix of the first one. Okay, let's keep this written here. Let's find the density matrix of this one, corresponding to this one. Okay, let's call it row 1. So what would be row 1? Oh my god, my writings are again going this thing. It's because of the perspective. Okay, so row 1 is probability. What was the formula? Qi times this thing, psi I. So Qi, what is the probability of 0? P0, so 3 by 4 times 0, 0. Plus for 1 over 4 times 1, 1. Now this is 0, so what is 0, 0? 0 0 is just this one. It's very simple, but I'm just doing it for the sake of this implication. 0 0 0 1. Okay, so my density matrix will just look like this thing. 3 over 4, 0 0 1 over 4. Right? Now the time to write the density matrix of this thing. Okay, so we have a certain way to pull this equivalency between two states given by the same density matrix. Okay, so it says that if you have two pure state ensembles with the same number of elements, okay, you have an ensemble with psi I states, okay, and the probabilities are given by these qi's, and then phi j is given by probabilities rj, and there exists a unitary u with it's a matrix u with the entries given by uij, such that you can write it like this: square root of q I times psi I is same as is equal to this, and if and only if, okay, this will happen like they correspond to the same density operator if and only if this thing happens, and the vice versa is also true. Okay, if they have the same density matrix, then this will be the case. This identity will be the case. Okay, and there is a proof for that, and I'll only do the if direction of the proof, which means that like if they have the if this is satisfied, then they correspond to the same density matrix. Okay, and the rest of the proof you can there is online. It's not I'm going to focus on the other things later on, so I'm just going to show that if this is true, then they have the same density matrix, and the other way around you can try to do it yourself. Okay, it will be good exercise. So this is my theorem. Okay, so the proof is something like this. It's a initial this density matrix, which is this thing, summation I q I psi I psi I. Okay, now you do this. You can write this also like this. Okay, summation I square root of q I psi I times psi I square root of q I, this way. Again, now we already gave the form in the last, when I before rubbing it, like if I can express it using a unitary operator, unitary matrix like this, j, let's say, sorry, and this is uij, and square root of rj phi j. If you can do this, then they have the same density matrix. Okay, so I am going to incorporate this thing in place of this thing. Okay, so this will give me summation I summation j, and there will be an inside here, it will be uij square root of rj phi j times, again, summation. We're going to use a different index because it's we already used I and j, so phi k. Okay, it's the opposite side. It's going to be ra, not a ket. And what did I do? No, I wrote it correctly, but I did this. Oh, it will be in the dagger form. Yeah, it will be in the dagger form because it's opposite, and it will be ik. Okay, so psi I is this thing, so psi I bra will be this dagger, and phi will come here, and rj is, it's a scalar, so it can remain anywhere. Okay, I can write it, and I can just group the summations like this: summation j and k times square root of rj rk times this summation I u ij u dagger ik. Okay, just grouping these and these together, the rj and rk together, and what is there? What is left there? Pi's are left. Okay, pi's will be this phi j times phi k. Okay, so what is this? This is just delta jk. This property of the unitary matrices is delta jk. So this will give me summation. Okay, so wait, summation j k rj rk delta jk times the phi's. So if I use the delta function, it will just give me this thing. K. Sorry, I can use any one, K or J. Let me use J since it's given here like this: phi J, phi J. Okay, so we got this. We got this. We took this density matrix and we got this density matrix. So it means that even though it's a density matrix representing a different ensemble, so I've just used this relation, and we see that using this relation, I'm coming from this density matrix to another form of density matrix, this matrix representing another ensemble, but they are actually coming out to be equal just because I used this substitution. Okay, so this is the formula, and it you have to prove it. Like, this is just one way of the formula, and the other way there is proof for that also, which I am not going to do now. Okay, now next comes the most interesting part, you can say, of this whole lecture. It's already big enough, but this part is the most interesting, and it's about the visualization. It's about visualizing the density matrix by taking, let's say, a qubit. We'll take a qubit and we will visualize the density matrix using something called the Bloch sphere. Okay, so before doing all that, I'm going to give you like the mathematical preliminaries to help you, to assist you to imagine the qubit using this Bloch sphere. Okay, so let's rub these things. Okay, so let's start. So visualizing the density matrix of the qubit. Let's write it as this one: visualization of the density matrix of a qubit. Okay, this is my section. Okay, so let's try to write the most basic form of the density matrix. And the qubit is, it's a two-level state, and it's a quantum state psi I in a two-dimensional Hilbert space H. There is C2. Okay, so let's just write it. Qubit is in a state. Qubit is a quantum state. Psi I in a 2D Hilbert space. Hilbert space. H is to C2, and the span, that is also the span of 0 and 1. Okay, yeah. So that is what my qubit is. Okay, and 0 and 1, they form the orthonormal basis for the qubit. I went through this, went over this qubit so many times earlier also. So density operator for any state is written as this summation qi psi I, and any so the density matrix uh, you can say that it can be represented as any two-dimensional matrix A B C D. Okay, so this is the most general form of a two-dimensional 2D matrix ABCD. Now we can simplify it even further. We can simplify it by considering the properties of the density matrix. Okay, so first of all, what do we know? We know that density matrix. First of all, we know that they have unit trace. And in this case, it implies that A plus D should be 1. So you can write that, you say that D is 1 minus A. Okay, and then another property, the second property, if you recall, the hermeticity. It just tells me that B is, these are each other's Hermitian conjugate. Okay, so I can say that here C is B star. Okay, so this comes from the hermeticity, and this comes from the unit trace property. And the third property was the positivity, which also implies that the eigenvalues have to be non-negative. Okay, so positivity. So using positivity, what do I find? Using this positivity property, which means that the eigenvalues will be greater than or equal to 0. So rho minus lambda I, the determinant of this will be equal to 0. Okay, the determinant of rho minus lambda I is 0. So let's try to solve it. That means, what does that mean? That if I write the characteristic equation, okay, plus determinant of rho is equal to 0. Okay, so if I solve this, I'll get these two equations for the eigenvalues. Half these two equations, I mean these two forms of the eigenvalues, 1 plus minus square root 1 minus 4 determinant of rho. Okay, so these are the eigenvalues that I get. They should always be greater than or equal to 0. So this condition is the positivity condition. Okay, so what do I get from this? We see that the new density matrix that I'll be getting from these considerations, D is 1 minus A and C is B star. So the density matrix, it will become something like this: A and then 1 minus A, and then B and then B star. Okay, so naturally one thing we know is that since trace is equal to 1, so the diagonal elements have to be real, right? They can't be complex. Okay, diagonal elements have to be real. So how many parameters do you have now? You can say that we have A and B. So for A we have just A, because A is real, and for B there are two parts. There is the real part of B and the complex part of B. Okay, since B and B star are probably not the same, so you can say we have three parameters to describe the density matrix. Now one is A, and then one is B, real part of B, and then the imaginary part of B. Okay, three parameters to parameterize density matrix. Okay, so we can now use this. We're slowly going to the realm of the Bloch sphere. Okay, so Bloch sphere is a 3D representation of the density matrix of a qubit. Okay, so it's connected. 3D representation and three parameters. It's connected. I'll show you. I'll just keep this form here. Let's look at the development. Now, uh, now we can say that any density matrix. Again, it's like a little theorem you can say, and it's actually quite trivial. So you can write. You can say that any density matrix can be represented in this form. Okay. So rho any density matrix is half of the identity plus summation I bi sigma I. Okay. So what are the V's? V's are just the coefficients. See, sigma i's are the uh, sigma i's are the Pauli operators, and V's are the coefficients of sigma I, and this is how you can represent any row, any row. So how does this really, I mean, make sense to anyone? This is actually the representation of row. Using this, rho is a vector, right? And now we have rho is in the vector in the Hilbert-Schmidt space. So this is the representation of the rho using the sigma operators as the basis, the sigma x, sigma y, and sigma z. So these are now my basis, and using this as basis, I'm representing rho. Okay. So how do I really? So this is how do I make sense of this? It's very simple. So another form of this actually means that it is half I plus V dot sigma. Okay, so V is basically Vx, Vy, Vz. Okay, and sigma is same as sigma x, sigma y, sigma z. Okay, so these are the V's and the sigma. Okay, so how do I write this? How do I like this part? So it's actually quite trivial. We know that any complex vector space, any any complex 2 by 2 matrix, they can be represented as an arbitrary sum of the identity and the those Pauli operators. Okay, so any let's do a little simple proof. So any operator, any 2D operator, let's say, it can be written as summation of, let's say, alpha 0 I plus alpha x, like alpha x sigma x plus alpha y. These are arbitrary. Okay, sigma y plus alpha z sigma z. Okay, now what do you have? This is for any particular matrix A, 2 by 2 matrix A. So density matrix, they have unit trace. Okay, unit trace. So which parts of these they have the diagonal elements? These and this and this. Okay, but we can have a density matrix where alpha z is equal to 0. Okay, because you can adjust actually the values of alpha, and this is a kind of this is not a proof, but you can make sense of it. So alpha z can be 0, and then alpha 0 would have to be what? Let's say if alpha z is equal to 0, then this one, what would be the trace of this matrix? It would be the trace of this part, alpha 0 times 1 0 0 1. That would be 2 alpha 0, and that should be equal to 1. Okay, so 2 alpha 0 should be equal to 1, so alpha 0 is equal to half. Okay, and if alpha 0 is equal to half, and then we can just put a half here, and then we basically got it formula. Okay, and all these things have to be real, obviously, because it's Hermitian, and all the sigmas are Hermitian. I is Hermitian, sigma x. So a dagger, if a is rho, and then rho dagger is equal to rho, so all these alphas, they have to be real. So is this V, they are also real. So this is like this is why I can write any density matrix in this form. It's actually a very important form. If you want to remember, you can note it down. It could be very useful. Actually, I'll write it somewhere also as well. So this is rho is half I plus b dot sigma. Okay. So this is how we make sense of this formula. Now, now using this, okay. So this is just bx plus sigma x plus. Using this, if I write the rho, it comes out to be something like this. The diagonal elements one, the first part in the sigma z, 1 plus vz, 1 minus vz, and that comes out to be vx minus iy, ivy, and that comes to be just using this one, right? Ivy. Okay. So from this we can know that what was our initial what was our parameterized this thing a b star and then 1 minus a. If we compare them, then we can see that here just b is just half of vx minus ivy. This is just a correspondence between the two forms, and then a is half of 1 plus bz. If you just equate the terms, you can get these. Okay. Now this v is what we call a Bloch vector. It's a very important thing again. This v is Bloch vector. Coefficients of the sigma x. When the sigma x is the basis. So this vi, I gave this one. Actually, I should have circled this one. These are the coefficients. So the same thing. So this v is the Bloch vector, which is this one. Okay. So the 2 by 2 matrix we've considered using the Bloch vector is it's actually not a valid quantum state yet. Okay, this quantum state is not valid yet. Okay, so unit trace is guaranteed by the construction, and positivity it can be now made explicit by noting that this thing. Okay, so what is the determinant of rho here? It should be 1 by 4 half to half, right? So 1 minus bz square minus 1 minus b square. This is bx square plus by square. Okay. Why am I doing this? Because if you recall, I am going to use the positivity property, and this formula for the determinant, it was there in the formula for the eigenvalues, lambda plus minus. Okay, so I'm going to use this formula for the determinant, the formula for the lambda plus minus. So what I get is, using this, if you just go back to your notes, you can see that lambda plus minus we will get from this is 1 plus or minus v. Okay, square. Okay, so using this rho, and what is I didn't simplify it. If you minus it, the minus things, it just comes out. So this is just 1 minus, this is just 1 minus mod v square, right? So 1 by 4 minus 1 by square. And if you use the formula which I found out already earlier for lambda plus minus, which went something like this. Wait, let me show you. So the formula for lambda plus minus, we found out already, it was half 1 plus minus 1 minus 4 rho. Okay, so using this or this here, we get this. So this is actually quite interesting, this formula. Okay, so this part, this is telling me that plus and minus eigenvalues should be this, but we haven't used the positivity yet. So what does the positivity imply to me? Positivity implies to me that lambda plus they should both be greater than 0, greater than equal to 0. So lambda plus greater than equal to 0, lambda plus greater than equal to 0 means half 1 plus mod p. I'm sorry, this is no square here. Square is here, but there is no square in this part. Okay, there's no square in this part. And then this is greater than 0. So it means that mod v greater than equal to minus 1. Okay, which is trivial because it's positive. So this condition is not really useful because it's obvious. And then another one is the negative minus 1. 1 minus mod v less than equal to 0. So that means that 1 minus mod v is 0. So this means that mod v or minus mod v less than equal to minus 1. So if I multiply minus both sides, so the sign will invert. So this means that greater than equal to 1. So this means that, so this, I'm sorry, did I do a mistake? Oh, I reversed the thing. I'm so sorry. It should be positive. And yeah, it's positive. And so this should be negative. Okay. So this is the condition. This is the condition for my block vector, the length of my block vector. It should be always be less than or equal to 1. Okay, it turns out that the length of the if the length of the block vector is equal to 1, it corresponds to pure states, and if the length of the block vector is equal to less than 1, then it corresponds to mixed states. Can we prove that? Can we prove that? Can we show that? Let's try. So, what did we know about the purity of a quantum state? I told you it's given by this quantity, trace of rho square. Okay. So for me, rho was this thing, half of I plus v dot sigma. Okay. So rho square would be certainly this multiplied by this. Right? What will this give me? This will give me something like 1 by 4. If I keep multiplying, then it will be 1 plus v2v times sigma plus this times this. So what will this give me? This is like v dot sigma square. And what is this v dot sigma square going to give me? It is going to give me this 1 plus 2 dot sigma, sorry, plus there will be two summations. Let's call it like this, k L belongs to x, y, and z. Okay, so this is vk, vl, and then sigma k times sigma L. Okay, it's natural. Okay, so this is what rho square will give me. Now, if I take the trace, if I take the trace of this thing, it comes out that if I take the trace of these parts, let's say, this is the half, and this is 1, and this is like, if I take the trace of this thing, it gives me trace of, let's say, trace of v dot sigma square. Okay, this is just, if you do it, you can see that it's just v square times trace I. Trace I is just 2 for 2D space. So you can get, like, if you do this calculation, you can get this. This rho square is giving me this. If I get the trace of this thing, trace of rho square, I get this thing, half 1 plus v square. Okay. So what do we learn in the last part? That v should be less than equal to 1. Okay. So let's talk about the, let's say, trace rho square equal to 1. Then if this is 1, what does this have to be? Yeah. It also has to be 1 then. Then if this is 1 here, then 1 plus 1, 2, half into 2, that should be 1. Okay, so that means that for pure states, this mod v should be equal to 1. Right? I feel too tired to write anymore. So this is just pay attention to this. This is the length of the block vector. Okay, this is when I represent the density matrix. The density matrix, which I write it as in this form, I'll represent it in this uh, three-dimensional representation where the Pauli matrices are going to be my axis, are going to be my basis, and the coefficient of the Pauli matrices, they are this. It's my block vector, and you can see that the length of the block vector, if it's equal to 1, then we get trace rho square equal to 1, which means that mod v equal to 1 corresponds to a pure state, and if mod v is much less than, mod v is less than 1, it corresponds to a mixed state. And what if mod v is 0? It's the maximally mixed state. Okay, so this is what we do using this Bloch sphere. Let me draw the Bloch sphere for your clarity. Okay, so the Bloch sphere is something like this. Okay, so this is, let's say, like this, and then this. Okay, and this. Okay, so this is the sphere. Okay, and it goes like this. I made a terrible drawing, I'm sorry, but it's something like this. So this is the coefficient. This will give me my Vx. This will give me my Z. Sorry, xy, and this is Vx. Okay, and if I, let's say, uh, I told you already the maximum length of the Vx, the maximum length of my V, the vector, the block vector, it can be only 1, because mod V is less than equal to 1. So the radius of this thing, it's actually 1, and so if you take from center to here, This represents pure state. Okay, so this is a pure state. Okay, let's say I take a vector from here to somewhere in the middle. Okay, so this is mixed state. And what if it's in the center? What is represented by the center? Right? It's nothing but the maximally mixed state. Okay? Okay. Now, this is what the representation of my vector in the Bloch sphere looks like. Okay. So let's do a little bit and then let's end it. Let's talk about the Z poles. Okay. So these poles. Okay. So what are these? What are the coordinates of these? My coordinates are the V's. Okay. So I'll write the coordinates as these things. So Z poles, which are this one and this one. So its coordinates are actually given by this block vector, which is 0 is its this thing, 0 x component and then 0 y component and then plus or minus 1 z component, right? Plus corresponding to this, minus corresponding to this. So this is the coordinate representation of my z poles, right? This is the coordinate representation. So what will the density matrix take form? Density matrix again is just rho of half 1 plus v dot sigma. Now only vz exists, vz only exists, and for this one, if I take v dot sigma, if I take this one, then it will be like 0 plus 0 plus minus vz z cap or whatever dot sigma z, right? So it will give me half 1 plus or minus sigma z. Okay, and what does it look like? It looks like very simple. It looks like for this 1 plus or minus by 2, 0, 0, plus 1 minus of plus by 2, 1, 1. Okay. How did I write this? It's very simple. If you write sigma z, it's just 1, 0, 0 minus 1. So I don't have enough space to do it. Let me do it in this little space. So sigma z is 1, 0, 0 minus 1. So this is the same as 1, 0, 0, 0 minus 0, 0, 0, 1. And this is the same as 0, 0 minus 1, 1. Right? And if you put like a minus plus minus in front of it, then this will become minus plus, and like this, using this you can get this formula. So for pz equal to 1 for this pole, then we have to choose 1 here, so this will get cancelled out and it will just be 0, 0, right? So this point is 0, 0. Let's do it in this one. Okay. Now for vz equal to minus 1, what will I get? Vz equal to minus 1, this one will cancel and this one will survive. So it will be this one. Right? Right. So this represents the 0 state and this represents the 1 state. Okay. Now for the x poles, let's do the x poles. This vector represents the 0 state, this vector represents the 1 state. Talk about the X poles. What are the X poles? X poles are these ones, this and this. Remember. So here, what are the coordinates of the Bloch vector? Let's try them. X poles. The coordinates are this v plus or minus 1, 0, 0. Right? So using this formula again, what I'll get is half 1 plus or minus sigma x. Right? Yeah. And if we do the same thing, we will get this one. If we evaluate it, what is sigma x using something like this? It's very simple. We'll get half 0 plus or minus 1 times 0 plus or minus 1. Okay, this times this. Now if I take plus, it will be this is actually a plus state. What is a plus state? A plus state is something like 1 over square root 2 0 plus 1. Okay, that is what you know as the plus state. If I take the Vx equal to plus 1, so it will take only the plus values. It will give me this. If Vx equal to 1, I'll get plus plus, where we know that the plus is just plus or minus is given by 1 over square root 2 0 plus or minus 1. Okay, now if I take Vx equal to minus 1, I get minus minus. Okay, it's very simple. You can see from here. So what does it mean? So this represents Vx equal to plus 1, it represents plus plus, and Vx equal to minus 1 represents minus minus. I can just write them there. So these points represent the different states, but I'm still writing in this density matrix form because that is more mathematically accurate, you can say. So Vx, that is the plus plus, this is plus plus. So this represents the plus state, and this represents the minus state. Okay. The same for the y poles, you know. If you do the same thing for the y poles, it will give me like vy equals plus minus 1. It's the same recipe. Vy will be plus or minus 1. So this one and this one. And using the same recipe, what we'll get is for vy equals 1, we'll get that this is this thing. Yeah, this will represent this bit. This is vy. Okay, so this will represent for plus 1, it will represent this state. 0 plus I 1 over root 2. Okay. This is get times bra or whatever, and then this one will give me, this one will be representing 0 minus I 1 over square root of 2. Okay, so we got all the poles. The plus or minus of z axis, they are giving me 0 and 1. Plus or minus of x and y, they give me plus and minus, and the plus and minus of y and z. Y for y, it's giving me 0 plus I1 by root 2 and 0 minus I1 by root 2. Okay, so these are the poles, different poles that I'm getting. So this is how you visualize the qubit. Okay, this is visualization of the qubit using the density matrix. Okay, using visualizing the density matrix of the qubit using the Bloch sphere. I'm sorry. So this is the end of this lecture, and in the next lecture we'll talk about how to combine composite systems of two Hilbert spaces, the interaction between a system and a path. So now we are going to really dive deep into the open quantum systems gradually. So after this, we'll go into the most important part of the initiation of open quantum system, which is the uh, operator sum representation using the Krauss operators and stuff. So, and then we'll eventually go on to the sweeter things like the linear master equation and all that. So tune into the next lectures. This lecture was huge, but if you watched till the end, it will be of great benefit to you. Okay, so thank you for watching, and see you later.